Hello guys, can you hear me? Very good, yeah. Hi. Hello. Good. Okay, so let me give the link. Other places and good afternoon guys, or rather good evening. Towards a good evening. Hello, yeah, hi. Hello, hi, good afternoon and good evening all of you. So I'm just waiting for the people to join. So hi. Yeah, I'm speaking. Can you guys hear me properly? Clearly? You cannot hear me? Oh, thank you so much. Yep. Okay, great. So yeah, sure. So yeah, I am telling and talking to you guys surely. So today we will be discussing something really interesting. Something that I already talked about last day in probability distributions seminar. Okay, and it was like just like not so rigorous talk. Just for us, it was just sort of stories out there. But now today we will like take this opportunity out to do some sort of rigorous stuff and see the whole thing about discrete and continuous together. Okay, and that's where it will become interesting. So when we will see that like the connection between those two, okay, that's the most interesting part that we will find out in today's lecture. Okay, so I'm just waiting for the people to join. There are a lot of people who told who will be joining. So essentially let's see some memes in the meantime and you enjoy them and let other people join. Okay, so yeah, that poor kid. True, yeah. So I personally believe that memes are really important to learn something really interesting, okay? To understand what's going on in the whole picture out there. So there is another one. I really like this one. Uh, I'm a fan of Big Bang Theory, so I personally like this one. Yeah, I am. Yeah. So do you know this person? Yes, you're right, Vishal. Yep. So that's the idea. So uh, yeah, I really like this one. And yeah, I thought of starting with memes because it sort of really makes us all like keeps us all on the same platform and the same page. Okay. Okay, it's no worries. Yeah, surely it's important. But let's leave it to the parents. It's we are what we are enjoying, guys. So if you see the like Big Bang Theory, Howard is that? He's like an astronaut, I guess. Cosmonaut is astronaut. Vishal. Okay, so let's start. So today, sort of, we are going to really be totally focused on yeah, cosmonaut. Yeah, cosmonaut. I realize now, cosmonaut. Yes. So today we will be focused on something uh, really intricate in the sense that this when I was a student in bachelor's in ISI. I was so I don't know whether you have been told or not, but with this thing, the subtle things which really make the subject and the ideas of probability distribution so interesting, was not really told explicitly in the manner, but they were taught. Okay, so one thing as I faced personally as a student, as a learner, both regarding this corresponding aspect of probability distribution is to remember this um, the corresponding like when to use it, how to model the stuff, what is the expectation, what is the variance, what is the blah blah blah. Okay, so that's really bothered me a lot. I thought that okay, I mean there should be an easier way to understand these probability distributions. Okay, and there should be something really interesting about the whole thing. And I started on like discussing and reading stuff and try to see the connections. Okay, and then I thought of like writing this down and sharing it with you. So that's why I'm today in here in front of you guys. So let's start. So today our topic really focuses on the probability distribution. It's a different perspective. The perspective I realized should be the idea of stochastic processes. Okay, I will not go into the details of stochastic process, what it is exactly, but I will touch upon it. Okay, so enough of memes for today, and let's move ahead to the actual discussion as of now. So today we'll be focusing on this set of six discrete random variables, and we'll see the connection between them. Okay, although they may not seem there, but they are connected. Okay, they are really connected. And we will focus on these three small simple continuous random variables. And like we will see that there exists an implicit connection, like explicit connection, sorry, between this, in fact, this continuous and discrete distributions. Okay, and you can maybe you can see from this small diagram. I will come to this simple diagram, we explain the whole thing out there. Okay, essentially this is the whole thing that summaries my discussion. Okay, and we will understand this in thorough details in today's discussion. Okay, that's my idea. That's what I'm going to help you out and share here today. Okay, guys. So let's continue with the idea of Bernoulli trial. So what is a Bernoulli trial? So it's a random variable which takes value 1 with probability p and the value 0 with probability q, and that looks like an odd person, like tossing a coin, right? So now it models what does Bernoulli trial model. It models the like possible outcomes with a single experiment that asks an yes or no question. That's it. Okay, that's how Bernoulli trials we use in real life. Now, what's a Bernoulli process? process means just a sequence of identically distributed binary trials. Okay, that means it's like you're tossing a same coin multiple number of times. Okay, or you're seeing a lottery winning or lost chances. Okay, or you're seeing the arrivals of the each like up like persons to the on to an airport, to a bank, to any server. Okay, like if you're if you're a blogger out there, then it's important for you to understand how persons are arriving. Okay, so this is important for modeling these cases, these real life scenarios, and also sampling with replacement is a Bernoulli process. Okay, okay, so now we will ask 5 questions. Okay, and these 5 questions will wholly summarize the aspect of these 5 questions will wholly summarize the aspect of the whole the lecture that we are going to do today. Okay, the whole discussion, and these 5 questions focuses on that how many arrivals. So suppose there's a Bernoulli process going on in front of you, okay, in the real life, and I will ask the question that how many arrivals, how many successors will be there among the first n Bernoulli trials. Okay, that's a really natural question to ask, right? And then I will ask another question that will that will go like this: that how many trials it will require to get the first arrival, the first success among this in this Bernoulli process that is going on. Okay, and then I will ask how many trials it will take to get the rth success from the r-1th success. Okay, or the arrival of that person. Okay, and then I will ask that how many trials it will require to take to the first arrivals, first R successes. And at the end, we will see that the solution to this last question, that among the first, suppose there are m successes and among their n trials are there, how many of the first n trials are successes? Okay, we will ask these 5 simple questions. And we will see that these 5 simple questions will lead to 5 simple distributions. Okay, and that's where this connection between all these distributions come up in this whole process. Okay, so essentially all these distributions you saw in the discrete part, they are a part of a Bernoulli process, and all the distributions you saw in the continuous part, they are part of the continuous process. Okay, that I will discuss. This is the Poisson process. Okay, so let's move ahead with this. So what is the Bernoulli process? A Bernoulli process is x1, x2, xn is a Bernoulli process where xi's are Bernoulli trials. Okay. Now, what was my first question? The question was how many successes will be there among the first n Bernoulli trials, and that is exactly modeled by the summation of xi. If xi is a success, it tells you that whether it's a success or not, right? Summation of xi will tell you it's a how many successes are there in first n tosses. Okay. And therefore we know that Sn follows binomial NP. Okay, that's the first step that comes up here. So first Bernoulli process, and we are asking the number of variables over here. Okay, and that's where the number of variables is modeled by binomial. Okay, binomial NP. Okay, let's see. So now we will go on to the geometric distribution, which is modeled by the following stuff. Suppose x1, x2, xn, and it's a Bernoulli process going on, and how many trials will require to get the first arrival or success? And that is modeled by geometric, right? I hope you have seen this, but maybe this on a connection to the Bernoulli process needs some explicit mention. That's why I'm here to help you out. So the number of trials required to get the first arrival is modeled by geometric P, and this is the way it's mathematically written over here. Okay, and that's where this summary comes up, the inter-arrival time. So okay, I'm coming to that part really soon. Yes, so now we have seen the first number of trials required to take the first arrival. That's modeled by geometric distribution. And now I ask the following question: how many trials it is required to take to the rth success from the r-1th success? Okay, and that is got by this it's called the inter-arrival time. Okay, the inter-arrival time means how many trials are required. It's just same, it's just like it is just there in the word inter-arrival time, right? So essentially what is the idea here is what we require is the idea of memoryless property, rather not the idea but the fact of memoryless property that is inherent in the geometric distribution. Okay, so it forgets stuff after what it has done till some point. Okay, and therefore if you have gone n steps in a Bernoulli process, then xn plus 1, xn plus 2, it's a Bernoulli process again, starting from new. Essentially, it's a new process coming up. It forgets the xnth part, okay? And therefore, if you go to the r minus 1th success and then you start again, right? It's essentially a new Bernoulli process, okay? So going from r minus 1th success to rth success is same as going from 0th success to the first success. That follows geometric distribution, right? So there it's called, therefore the interval time comes up here, and therefore the memoryless property plays a really big role over here, okay? And that's how the interval time is modeled by geometric distribution, okay? It's much a general, more general definition than the number of trials required to get to the first success, okay? It's a if you put r equal to 1, that's what you get, okay? Okay, so what's next? Next we will attack the question of how many trials it is required to get to the first rth success, okay? So we have seen that it takes each of the geometric random variables is modeling the r minus 1th to rth success time interval, right? So the total time required to go to the rth arrival will be sum of this. So it will be t0 to t01, that is the time of trials required to go from 0th success to the first success, and then t12, that is the first success to the second success, and it will sum of it, right? The number of trials required, and each of them follows independent geometric p, okay? And the summation therefore will follow the negative binomial, right? And therefore this question is answered by the negative binomial aspect, the negative binomial r comma p to get number of trials required to get the rth success, okay? Okay, everybody on the same page? Any doubts of you understanding, right? Any doubts, guys? Okay, so I will move ahead. Now observe that I will go to the last question, and that's what is answered beautifully by hypergeometric distribution. So this is what really attracted me about this process, okay? So we are like, so hypergeometric was one of the distributions I really dreaded in my college life, okay? But after seeing this, it felt so natural to me. I hope it will feel natural to you too. So x1, x2, xn is a Bernoulli process, and I asked the final and the foremost final and the most important, but the most creative question, that suppose there m success among the first n trials, okay? And now how many of those among those trials, how many of them are successes among the first n trials, okay? Small n trials. You see the subtleness here. So there are it's given that among the first n trials there are m successes, okay? Now you're taking the first small n trials. How many of them will be successes, right? That's what is actually measured by the hypergeometric distribution, okay? And this I denoted by h n comma m comma n, small n, and this follows hypergeometric n comma m comma n. If you think carefully, it's just like that, selecting those black balls and red balls out. So among those m, so there are m white balls and n minus m black balls, okay? And you're taking out n balls, small n balls, you're asking how many of them are black balls or white balls, whatever your success is, right? That's exactly the hypergeometric distribution, okay? And I will add a little bit more point to this, that this hypergeometric distribution is actually going towards the negative, the binomial. Okay, so hypergeometric is models, is used to model the sampling without replacement, okay? And binomial models sampling with replacement, okay? So therefore, if you make the sample, the population size so large that the sample doesn't matter, the sample size doesn't matter. So that is also that proportional probability is going towards a constant. The amount of probability, like m by n, is the amount of success, right? That is going to a small constant p, that is a probability success. And the small n, the sample size n, is held constant, the number of trials rather, in Bernoulli, in binomial. Then this hypergeometry will go towards binomial, okay? And it seems so natural, right? The population is becoming so large that it's sort of sampling without replacement, and with replacement becomes sem. And this sort of intuition we all have inside us, okay? So this is where I this is the idea, the connection between all the aspects of the binomial, the Bernoulli, the hypergeometric, the negative binomial, geometric, all together, okay? And this is totally and beautifully modeled by the aspect of the Bernoulli process. It comes naturally out of the Bernoulli process, okay? That's what my point is to you. Okay, so what we have got at this like till this point, we have got the following. So we have a Bernoulli process. The number of arrivals is modeled by binomial. The interval time is modeled by geometric. The trials for the number of trials for the rth success, the rth arrivals is modeled by the the negative binomial, sum of geometric. And what is hypergeometric? It's actually a rote thing because there is not enough space to write, but you understood that we are fixing the population side, we are fixing the success too, and now we're taking a small sample out of it. Okay, that's what is modeled by hypergeometric. Okay, so this is what a discrete processes look like, and how all these distributions come up naturally in the process of asking these simple 5 questions. Okay, all of you understood it or not? Because now the next part will become super easy for you. All of you on the same page? Any doubts, guys? No, I guess. Okay, so let's continue. Okay, so let's continue to the next part, the Poisson process. Okay, so what is a Poisson process, guys? A Poisson process, you can think of it is used to model like, it's just, you can think of it like Bernoulli process ka limiting condition. Okay, where the number of trials is so large and the time distance between these small trials are 0.001 millisecond. Okay, they're so small that it becomes continuous. Okay, in that sort of sense, and that we will prove here by a certain methodology. Okay, so stay focused. The counting process NT is called a Poisson process. Okay, but obviously n0 is the time that at time 0 there are 0 such countings happening. Okay, so you can think of it like you have the counter which captures the radioactive materials. Like there was experiments which I use in physics. Okay, I forgot the name, some G counter. Okay, and think of it like that, it's counting as time is going on. Okay, and it's had independent increments, and the number of countings, number of events in that, consider that an event. Okay, here we will replace the arrival and success by an event. Okay, and we will see an example soon. So these events is proportional to the size of the length of the time, like size of the time length. Okay, that's the idea, and this is mathematically written by this, that follows Poisson lambda t. Okay, but this is like the definition of it. We will come from a more natural, intuitive aspect. Okay, so suppose, like, consider this bus scenario. Okay, the bus is coming towards the bus stop at this time point, and it's like this: at 0th time point, it is 0. Okay, number of counted events is 0. The process of independent increments. That means that if the number of buses that will come after 15 minutes, the way it will come will be same as at the beginning. Okay, the number of buses, how it will come after say 2 days, it will same as 0th time point. Okay, not 2 days. 2 days is a bit longer, but maybe 1 hour or 2 hours seems totally realistic. Now, what does the last 2 means? Probability of nh is equal. So for a small interval, it means that for a small interval, the probability of getting one event is really there, but probability of getting more than one event is really too less, very zero. It's 0 almost. Okay, and probability of getting one event is proportional to a constant lambda to the size of the time interval. Okay, this is what is modeled by Poisson. Okay, and we will see that more Poisson process. Actually, we will see how this is sort of being naturally described as binomial stuff, and how this is like slowly limiting towards a Poisson process. Okay, we will see this clearly. Okay, so let's move ahead. Okay, let's move ahead. So, okay. So now how we will now go towards a Bernoulli from the Bernoulli process to the Poisson process. Okay. So now consider this. Let's focus on this diagram. Okay. So you have this time interval tau, and which is counting the arrivals. Okay, arrivals of the events, or it's counting the events. Okay, and counting the arrivals of x, which is the event here. And we are partitioning the n lengths, n such partitions. We are partitioning the whole length time interval tau. Okay, and obviously each equal partitions, and obviously each of them is of the form like delta. Okay, it's tau by n, each of the partition length. Now what we have told, for a small time interval length, the aspect, the total number of countings that will happen in that will be 1, right? So will be 1 in the sense that the probability of occurrence of one of these like one event in each of this interval length is proportional to the length of that tau, delta, okay? And the proportionality of occurrence of probability of occurrence of more than two events, more greater than equal to two events, is actually 0, okay? So sort of in each of this interval, it's sort of a Bernoulli process, right? Each of these intervals of the Bernoulli process. And what is the probability? The probability of the process is actually per period, it's lambda, it's proportional to the lambda into the delta size, right? We have what we have done here. The probability of success of one event is lambda into h, and h here is delta, right? So therefore its probability of success is lambda delta. Delta is equal to tau by n. So probability of success is lambda tau by n, right? So therefore we get this expected number of intervals is np is equal to lambda tau. Okay, that's the idea. So now think about this very carefully. So in each of these intervals, in each of these n intervals, it's a Bernoulli process, right? With probability lambda delta. Okay, probability p that's written over on the screen, and the number of events in this all this total time interval tau will be what? Will be sum of all this, right? Right? And sum of all this is binomial n comma p, right? So it's binomial n comma lambda tau, right? So remember this. So each of these intervals ni is binomial n comma lambda tau by n, okay? Lambda delta, which is tau by n in each of this interval, right? Number of counting processes, right? And we know that this intervals are going very small and n will become large, and therefore this will converge to binomial n p, right? Which is lambda tau. And that's how this Bernoulli process is converging towards a Poisson process. So essentially, how is the Bernoulli process coming up? Each of this interval is a Bernoulli process. Okay. Now we are making this interval so small that this Bernoulli process is converging to a Poisson process. Okay. This is the beautiful idea of convergence of Bernoulli process to the Poisson process. All of you understood this basic idea, guys? Any doubts in this? So we are seeing that this Bernoulli process in each of these intervals, it's becoming so small that is going towards Poisson process. Okay, that is this small number of events in this time interval length is being modeled by Poisson lambda tau. Okay, that's the basic idea. Okay, guys, very good. Let's move ahead. Okay, so what you're trying to project, see here, very crucially. So understanding each of this, so what we are telling here, that probability of one event is proportional to lambda h. The probability of this means that it's close towards 0. It mathematically means that probability of more than two events, two or more than two events, is 0. Okay, you can think about it. Therefore the probability of one event is this lambda. Therefore the probability of success is lambda into h. Okay, therefore in each of this interval the probability of success is lambda into h, which is h is equal to what? That is delta here, right? Delta is the length of this interval, right? What is delta? Delta is equal to tau by n, because we have divided into n intervals, right? And therefore the probability of success per period is lambda delta, which is lambda tau by n. And the number of events in all of this will be summation of all these ni's, right? Naturally. And therefore which will follow binomial n comma lambda tau by n, right? Which will go towards Poisson lambda tau. Okay, that's the Poisson process that is coming up here. Okay, and we will see that when we will move from the motion, like we will move towards Poisson process from the Bernoulli process, we will see that this number of trials will slowly converge towards the question of how much time it's required. Okay, that's the idea. Okay, so I will move ahead now. If you have no doubts as of now, I will move ahead to the, yeah, very good. So I will move ahead to, yeah, Pawan. Did you understand, Pawan? Or should I repeat? So from this Bernoulli process, I will slowly move towards Poisson process. I have moved towards Poisson process. Now I will ask similarly 5 questions out there. Okay, everything will be simply clear. Okay, that's the idea. Okay, so let's move ahead. So similarly, I will ask this similar 5 questions in this Poisson process. Okay, so there were how many such events? Okay, so there were, what was the first question in that binary process? Remember, how many arrivals will be there among the first n binary trials? That is replaced by how many arrivals will be there in the first time t. Okay, so as I told that how many trials, number of trials will replace by how much time. Okay, so discrete part is being changed to the continuous part aspect of time length, and how much time it will require to get the first, it was how much trials it was required. Okay, here it is required how much time it is required to get the rth event from the r minus 1th event. There it was how many trials would have been, which I would have taken. Okay, here it is how much time to get the first rth events. There it was how many trials, and similarly here's the last most exciting part. Given that alpha plus beta events have occurred in the time interval length, what is the fraction of that interval until that alpha event occurs? Okay, there it was similar sort of thing. Okay, these are the 5 questions we'll ask now, and these 5 questions will lead us to the whole continuous, this whole set of continuous distributions that we are interested in. Okay, so let's move ahead one by one. So what we have seen, Poisson distribution is a like continuous aspect of boundary process. So if you ask the question how many events arrivals will be there in the time t, it's sort of binomial, sort of going towards Poisson. We have seen that, okay, in that previous discussion. Number of arrivals in the time t is actually being modeled by binomial for the discrete case, which is going towards lambda t. Okay, Poisson lambda t. Okay, that's how we are counting the number of events in the first time t. Now next one, the exponential distribution comes out of nowhere. Okay, so if I ask you how much time it is required to get the first event arrival, actually the continuous version of the exponential, the geometric distribution is the exponential distribution. Okay, and we'll see that it follows exponential lambda. Okay, it follows exponential lambda, where lambda np is going towards lambda, and next we are taking as k by n. Okay, guys, that's the basic connection between this geometric and the exponential altogether. Okay, so do you have any questions, guys? I would like to answer some of your questions, guys, if you have any questions. Otherwise I will move ahead. This is the beautiful connection between all these probability distributions together. Okay, this is the beautiful connection between all these probability distributions together. Okay, I'm moving ahead, guys. Then any doubts, Hemant? You have any doubts, guy? Hemant? No, I guess. Okay, I will move ahead. So now let's come back to the aspect of inter-arrival time. Okay, we have seen the first arrival time is geometric p for the discrete case, which is going towards exponential lambda, because mp is going towards lambda, and x is like we're taking that portion to be x is equal to k by n. But essentially, it's sort of becoming so close that geometric p is becoming exponential lambda. And now it's natural question asked, what was the last question there? What was the second last? Not the second last. The second question out there. The third question, sorry. How much time it will take to get to the rth event from the r minus 1th event? Just the extension of the first arrival time. It's the rth arrival time from the r minus 1th event. Okay, and that was done by geometric p in that same case, in that aspect of geometric p, like discrete process, boundary process. But here it's exponential p, exponential. Oops, it will be exponential lambda over here, and it's essentially it's same, like it's geometric p and it's going toward exponential lambda, and it has a memoryless property. Exponential lambda has a memoryless property. Okay, same thing. It's essentially just written in different words. Okay, just try to connect these whole things together. Okay, and then we have the gamma distribution. What is the gamma distribution? The gamma distribution comes up as a summation of Poisson, a summation of this exponential. Okay, and so if you ask that how much time it will take to get the first rth event, okay, and that will be sum of exponentials, right? Just like in the discrete is a sum of geometric, which gave to negative binomial. So here it's sum of exponential, which is giving like gamma r comma lambda, which also known as L-Lang distribution. Okay, and because when r is equal to integer, it's called L-Lang distribution. Okay, and therefore this exponential. So geometric a continuous version exponential. Therefore, negative binomial continuous version is gamma r comma lambda. Okay, negative r comma p is same as gamma r comma, not same but continuous part is gamma r comma lambda. Okay, that's the gamma distribution coming into the whole picture. And then we have the beta distribution, the last one, that given alpha plus beta events in a time interval, it's we know already it had occurred. In the discrete case, it was given there are m successes among the first n trials. If we take out small n samples, how many of them will be success? Here we are asking, given a plus b successes have occurred in a time interval, okay, then because time interval t say, then what is the fraction? As I told in my classes, that we are seeing probability here. Beta distribution is a prior for Bayesian, for in Bayesian statistics, a prior for probabilities, right? So here we will not ask number of success, we'll ask the probability of success. Okay, so here we'll ask what fraction is it is there until the alpha event, alpha success occurs. Okay, that follows beta alpha comma beta. Okay, and that's the beauty of this. So essentially we come to the last summary of this, that if the whole thing, the whole thing is being modeled by this like simple stuff, simple one figure summary. So we have two processes going on. Bernoulli process, we're asking number of arrivals over there, okay, and we're asking it's coming out binomial. We're asking the inter-arrival times, it's coming up geometric, okay, and we are asking for the number of trials for the r arrivals. It's coming out negative binomial, summation of geometric and negative binomial. Then we are asking that what is that hypergeometric question. Okay, yep, you understood that. Now for the same case, now Bernoulli process is going towards Poisson on the right hand side, okay, and we're asking the same question, number of arrivals in time t, it's giving Poisson. We are asking the same thing, that number of inter-arrival times, okay, from the like number of inter-arrival time, okay, not number of trials. Okay, it was on the left hand side Bernoulli process scale, it was inter-arrival number of trials. Right hand side it is inter-arrival time, it's continuous part, it's coming exponential. So binomial ke liye Poisson, exponential is going towards binomial is going towards Poisson, geometric is going towards exponential, negative binomial is going towards gamma, hypergeometric is sort of going towards binomial, which is going towards beta. Okay, that is the basic idea, that is the basic connection between all this together, guys. Okay, that is being subtly described by this single picture, and this is what I have to offer to you today for understanding these probability distributions from a different perspective that is not usually followed in our exactly. One is trials, which is discrete one, and one is time, that is a continuous one. Okay, this is what hypergeometric example. What do you mean by hypergeometric example? What do you exactly mean by hypergeometric example, guys? So hypergeometric, as I told, it's this model. Okay, suppose you have n trials, okay, capital N trials, and you have out of them m small successes. Okay, and out of those you are taking out the small n number of trials out there. Okay, so my question is that how many successes you will need for the hypergeometric one out of the small n trials. So let's go back. Sure. You want the hypergeometric one? Let's go back to hypergeometric one. So what is the hypergeometric one? We're asking that there are m successes, okay, among the n capital N trials, and now I'm taking a small n trials out of those. So think like close your eyes and think in your mind eye that there is a ball. It has capital N number of balls. Out of them, m number of white balls are there, capital M, and you're picking up. You're picking up your big hand. You're going to that ball, and you're picking up your closed eyes, and you're picking up handful of say 10 such marbles, and you're seeing that, asking the question that how many of those marbles are now whites. Okay, that is modeled by hypergeometric. Now for the Poisson process, for the continuous part, it's asking the same manner, that now close your eyes again and think in your mind's eye that you have a time interval for 1 hour. You're standing at the bus stop, and you from your past experiences that alpha plus beta, say 5 plus 6 buses has arrived in this time interval. Okay, now asking that what is the fraction of interval until that the first alpha event 5 passes have occurred. Okay, what is that time? Okay, because it may be of some importance to you, or maybe you can think of alpha buses or 5 taxis will come. Okay, so you are now you are wanting to go to the via taxi. Okay, and you wanted to go not via bus. Okay, suppose you know that buses have gone, so what is the fraction of the interval that until that alpha event occurs? Okay, this is the motivation behind beta distribution. Okay, and this comes up naturally out of this procedure. Okay, this is the beauty of this whole process. Okay, so any doubts now, guys? I hope all of you understood this one. Any doubts? So I've tried my best to connect this continuous and this whole aspect of discrete and continuous distributions together in a single framework of stochastic process. Okay, very good. So thanks for attending the live session, and very good. So I will discuss about this more in details in our classes today, Hemant. But regarding the more of the mathematics and more about these individual distributions. But yeah, so this is what I wanted to offer to you guys. I hope it has helped you, and it was really nice being with you guys. So thank you so much, and don't forget to subscribe. Okay, and stay tuned for our stay tuned for our next session. Okay, bye bye and see you. See, normal distributions is not really a part of this, what I wanted to tell. It's a part of the central limit theorem, okay? So maybe it will be a part of the next lecture, next session that I will take power on, okay? That's the idea. Okay. So bye-bye and stay safe, stay blessed. Bye.